Today, we're taking a look at Go Ethereum, an Ethereum implementation written in Go. This is Answer Everywhere, and we explore source code. We will put it on a timer for 30 minutes because we are doing 30-minute time box sessions just to see what we can find in an initial exploration. And we have looked only at one cryptocurrency implementation so far. We've looked at Bitcoin, Bitcoin Core, you might call it, and not just any Bitcoin Core. We looked at the original Satoshi code, and this will be the second of the cryptocurrencies. And you can donate to Answer Everywhere, and I'll put an Ethereum link in the description. And there's also Monero links and Bitcoin links, if that's your thing. So we'll see, this is Go. So we've looked at a few Go things before. We see a tree here, which is a little bit interesting. Is that interesting? I'm not sure. We see Swarm, RPC, P2P. I don't know what RLP is going to be. Some params is probably not so interesting. Node might be important. Miner is important for mining. There's some GraphQL. For what? I don't know. Maybe there is I don't know. What? I guess we might as well open GraphQL. We only have 30 minutes, so we're not going to see all of this stuff. Event, ETHDB is presumably going to be some version of a database that's used to store the blocks, although maybe not. ETH client is going to be presumably the client for the blockchain. ETH, I don't know what will be in there. Crypto will be crypto. Core. Common. Command is probably going to be command line support for the CLI, but it could also be like maybe the command pattern, or it could be possibly related to the opcodes for the Ethereum machine. Beacon, I don't know what beacon will be, and accounts. And I guess all of these seem pretty interesting, at least mildly interesting. So we'll fly through them and try to find the coolest stuff. We do see a table of executables. Geth is our main Ethereum client. It is the entry point. Our main Ethereum client. So our probably means Ethereum. So I'm guessing they're saying that Geth is in general the main Ethereum client. So best Ethereum client. Let's just verify this. So there's Ethereum JS. It's written in TypeScript. So Geth is one of the original implementations of the Ethereum protocol. I didn't realize it was originally written in Go. Let's ask ChatGPT, what language was the first Ethereum client written in? Okay, so this is the first Ethereum client. Okay. And the obvious question is, why not Smalltalk? Go is known for its efficiency and performance. Is it? I guess concurrency, people like the Go. Yeah, all right, fine. People like the Go, whatchamacallits, the lightweight threads. I forget what they're called, Go routines. All right, so we also have Clef, a standalone signing tool, which is it's used for signing stuff. Dev P2P, utilities for interacting with nodes. Abigen, source code generator to convert Ethereum contract definitions into easy-to-use, compile-time, type-safe Go packages. Boot node, EVM. I don't know if these are all in this current repo, but I guess they must be. You need you need a CPU with 2 cores to run Geth. Okay. So this is some try implementation. And we have node and proof and go. Node and proof and what was it? I don't know. I don't know what I was thinking. I was looking at that I read go instead of the thing. So that's a little bit interesting. So this is perhaps this is related to the block structure itself. We have a Verkle, which I'm going to guess is a variant on Merkle somehow. New Verkle try constructs a Verkle tree based on the specified root hash. So let's look up Verkle tree. Verkle trees are key value pairs where the keys are 32-byte elements composed of a 31-byte stem and a single byte prefix. These keys are organized into extension nodes and inner nodes. Okay, so this has kind of like a try-like structure. And I guess it's like a combination of a try with a Merkle tree. So Verkle try, vector-based proving scheme, Merkle tree structured after a Merkle tree, and retrieval organized by key for easy retrieval. Okay. So we'll come back to this because if we get into that, I think we're going to be there forever. So TryDB has a HashDB, a PathDB, and a database. You have database.go. I'm going to guess this is some on-disk key value store similar to BerkeleyDB or LevelDB or RocksDB. I don't know if they use one of those or if they're making their own based on this try stuff. We've got this Verkle default backend. We have some interface, whether it's initialize, size, update, commit, close, etc. Are they importing anything interesting? Mostly, in fact, entirely Ethereum stuff. TryDB. Okay. So what database does TryDB and Ethereum use for storing? Does Ethereum use for storing blocks on disk? Is it a standard on-disk database, or did they create their own? I'm guessing they created their own, and that's what we're looking at. Oh, it uses LevelDB. Is that true? Let's look for LevelDB. We do have LevelDB. We have FDB. Okay, so FDB has a LevelDB package. And do we include something? We're including SynDTR's Go LevelDB thing. I don't know what SynDTR is. LevelDB is a Google thing, but this looks like a non-Google non-Google library. By this dude. Okay. So, I hope this is a good implementation of LevelDB. All right. So that's FDB. Let's look at the root FDB. So we have LevelDB, DB test, Pebble, memory DB. I don't know if Pebble's a joke on RocksDB or RockDB. So we've got CockroachDB Pebble. I don't know if these are alternate DB implementations or if we're somehow using them together. Pebble. Pebble is a LevelDB/RocksDB inspired key value store based on performance and internal usage by CockroachDB. Pebble inherits the RocksDB file formats and a few extensions. Okay, so it's a CockroachDB's spin on LevelDB. So how is Pebble How's this going to be different? We have a database struct. Let's see. This is maybe a question for the documentation. So let's try Ethereum. Go Ethereum level DB Pebble DB. Databases. Geth has divided its database into two parts. Recent blocks and state are kept in quick access storage, but older blocks and receipts, I guess which are called ancients, are stored in a freezer database. Okay. Let's see. So this is to minimize wear on SSDs. Storing less data in the faster level DB database also enables faster compactions and improves database performance. Okay, so which one is which? So level DB, I guess, is the faster one. And then which one is... It is possible to configure Geth to use Pebble instead of level DB for recent data. Okay, so what is the... It sounds like It sounds like Pebble DB is an alternative to level DB. But then what is the default slow DB? So recent blocks, blah, 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 freezer ancients. Older segments of the chain are moved out of the level DB database and into a freezer database. But what is the freezer database? Okay, let's ask ChatGPT. What does Go Ethereum use for the freezer database? A custom storage solution called Ancient. All right. And then let's also check Geth TryDB. Not finding it. Okay, so that's databases. That's what's up with databases. Pebble and LevelDB are like on the same level, and I guess MemoryDB is similar. Let's see if we can find ancients. In database, well, we have ancients in database.go. We have also raw in rawdb. So what is rawdb? We get a no, we don't get a comment or a README. But this seems to be the freezer implementation. We've got some table. I don't know if we import anything interesting. We're just importing ethdb. That's not going to work. Okay. So here we are in TryDB, which I think is where we started. Do we import ethdb? Yeah, we do. So TryDB seems to be a level above ethdb. Ethdb is essentially probably a pretty thin layer on top of level and or rocksdb and or pebbledb. And this is going to be, I guess, the thing that stores tries and uses the level DB as storage. And I'm just going to assume that's what it is. Swarm, ETH Swarm. Swarm is a distributed storage platform and content distribution service, a native base layer service of the Ethereum Web3 stack. It's moved to this thing, EtherSphere/B. Okay, so it's not part of my mandate if it's in a different repo. That's what I decided. And here's RPC. Oh yeah, now I'm remembering with Bitcoin, it's set up as an RPC protocol. So you send RPCs from the command line tool sends RPCs to some server, and the server is the thing that I guess communicates to the other nodes. So in the original Satoshi Bitcoin code, the way it worked is it communicated over IRC, at least to bootstrap the original, the initial downloading of the other like IP addresses of other nodes. And so that's a service. And then the command line tool is just like runs one command, sends it to the service, gets a response and prints it essentially to the console. And so that's what I'm going to guess is going on here. Although we do, so server, this is, I guess, is the RPC server. what are we using for RPC? Maybe we're just rolling our own. We've got some mutex and a server codec. A new server is going to create a server with its ID will be some random ID generator every time we run, I guess, and a bunch of other stuff. We're going to run server.run.store true, and we'll set RPC service to be this RPC service that consumes a server. But where are these things defined? The server is a struct here. We've got some service registry. And I would just kind of like to see, like, are they, presumably they're using the standard HTTP server. And then where's the RPC server? RPC service. It's a struct that just has a server. RPC service gives meta information about the server. For example, gives information about the loaded module. You can ask it about modules. Here's a peer information struct that's got some transport. And the client can communicate, I guess, using HTTP, WS, which is presumably WebSockets and IPC. So see if we can find where they're importing HTTP. We've got rpc/http.go. And we're importing, okay, here we go, net HTTP, net URL. So this is the, this is just going to be the implementation, I guess, of the HTTP service. Relying on the Go HTTP stuff. All right, so here's PTP. We've got Discover, which is probably mildly interesting. DNS disk. I don't know what DNS disk is. DNS Discover, perhaps. eNode, maybe Ethereum node. NAT will maybe be for NAT traversal. Let's look at peer.go. We've got some variables to do things like store the protocol version, protocol length, snappy protocol version, whatever snappy is, and some message codes like the handshake message, ping and pong. A proto handshake is the RLP structure of the protocol handshake. Okay. So all right. So somehow, so this is like the peer protocol. This is pretty interesting. I guess we're gonna maybe send JSON. And then the question really is, how do we find peers? And let's just verify that NAT will be NAT traversal. NAT.go. An implementation of the NAT.interface can map local ports to ports accessible on the interface. You can add mapping, delete mapping, external IP. You can parse a NAT interface description. You can map. I don't see anything about traversal. Let's try just a web search. How does an Ethereum node traverse NAT? For true decentralization of an app, a point-to-point internet connection without a centralized signaling server involved is a must. But having looked through all the various Ethereum node/clients code, there is often a signaling server or relay nodes with ports exposed to external network involved. Bitcoin trackers are basically signaling servers, and no one has been able to censor all of them for decades. PDP protocols also usually implement UPnP for NAT, though I've never seen published what % of internet users it works for. Also, signaling protocols like STUN and E2E are encrypted. How could they censor you? All right, so I guess I did see UPnP, didn't I? Let's find that again. Yeah, so we have NAT UPnP. And I'm going to guess that this is where the support for traversal is, because it seems to be supported by UPnP. eNode, I don't know what eNode is, but maybe, I guess, the Ethereum node. Package eNode. So a node is a struct that has a record, an ID, some endpoint information such as an IP address, and UDP and TCP, which are uint 16s. We can wrap the node record. So we can check whether, so we have this valid IP thing, which we'll check whether that's valid IP. And we do some IP validation and we verify that it's not multicast. I guess you can't have a multicast ID. And then we can locality score an IP address, which will do what? If it's loopback, then we return 1. That's probably the best score, the most local. It might be a link local unicast. It might be private. And default is 4. So private, I'm going to guess, means it's on your private network. It's one of the like private IPv4 blocks. I don't know if they support IPv6. DNS disk, I decided it was probably going to be Discover. DNS Discover. Let's try client. So we have some configuration options for the client, like timeout, recheck interval, cache limit, rate limit. We have a resolver interface, which has lookup txt. And we have things like rate limiting. I still don't know what we're really doing. We have sync tree, which downloads the entire node tree at the given URL. Okay, so node tree. So I'm guessing what we're doing is we're maybe asking other nodes for the nodes that they're connected to, perhaps. Resolve root tries to resolve a root entry via DNS. And I'm not sure. Updating DNS discovery. Let's look up get DNS discovery. DNS discovery setup guide. How to set up an EIP 1459 node list using the dev PTP developer tool. Node discovery via DNS scheme for authenticated updatable Ethereum node lists via DNS. So this is some proposal they had for extending Ethereum to support discovery via DNS, and this is the DNS disk is the implementation of it. And that's about all I'm going to look at for PTP Discover. RLP, I don't really know what RLP is. Recursive length prefix serialization. It's used extensively in Ethereum's execution clients. RLP standardizes the transfer of data between nodes in a space-efficient format. But why not use an existing encoding? The purpose of RLP is to encode arbitrary nested arrays of binary data. And RLP is the primary encoding method used to serialize objects in Ethereum's execution layer. Okay. I'm sure they have a reason for this, and I'm not really even going to ask about it. I'm sure there's lots of information about RLP. I don't know how it differs from the many other encoding formats that they use, for example, in the financial industry or elsewhere to rapidly encode and decode data. But maybe because of the nature of Ethereum messages, they need a specialized, or at least slightly different way. Params, I'm just going to ignore. Well, we have DAO. What is DAO.go? DAO fork block extra is the block header. We have a DAO drain list is the list of accounts whose full balances will be moved into a refund account at the beginning of the DAO fork block. Huh. What was the DAO thing again? Decentralized autonomous organization. So what is the fork? The DAO attack. Understanding what happened. There was some attack, and I think that they basically patched Ethereum to deal with it. Finalize the DAO fork. Oh, I guess they like forked it because they didn't like the way it was going or something along those lines. All right, so here's the node directory. We have API, endpoints, etc., errors, jot. I don't think that that's what we really want to see. We have only about 4 minutes left. Miner. I think I'm going to skip miner. Internal, we have like block test, shutdown check. We'll ignore that. GraphQL. We're limited on time, but I'm just kind of curious why they even have GraphQL. They have support for some, I guess, in-browser IDE for exploring GraphQL APIs. I don't know, some JavaScript stuff. Event. I'm not going to look at FDB. We looked at eth-client. I'll ignore eth. Has what? Downloader, gas estimator. That might be interesting. Gas price. Protocols. Fetcher, downloader, catalyst. Bloom bits is maybe some kind of Bloom filter. Handler is some kind of maybe handler. Peer.go. Something about peers. I don't know what catalyst is, but we have a queue, a simulated beacon. Let's see what an Ethereum beacon is. The beacon chain. The beacon chain. Introduce proof of stake to the Ethereum ecosystem. Okay. So, seems maybe something about the move to proof of stake. Here's crypto, which we've seen crypto recently. I guess we have so few minutes that we'll see if there's anything more interesting. VM, core/VM. This is probably where we really want to see. We have gas table, instructions, interpreter, a jump table, memory.go, and opcodes. In operations ACLs, in operations Verkle, and a stack table. So we'll look very quickly at these. Opcodes, we have things like stop, add, subdiv, sdiv. I don't know what sdiv is. Maybe, I don't know. I'm not going to guess. Less than, greater than, is 0. And like account related stuff looks like address balance, call data size, ext code size, return data size. These are just defining the opcodes as specific numbers. And then a bunch of pushes for pushing things onto the stack, dupes for duplicating, swaps, I guess, for swapping things on the stack, logs for, I guess, logging, and some range closure stuff. So like call code, return, delegate call. So I think this is maybe a big part of what makes Ethereum different from Bitcoin, is that it supports functions, I think is the idea, is that it has more behavior. And I'm guessing that that's related to this. So we have call, presumably call a function, maybe create a function, call code. I don't know what call code is. Delegate call, return, perhaps return to some function, static call, revert, and so on. And to avoid the problem of the question then is if you can execute arbitrary functions. The question arises of what of how to account for resource usage, and that's where like gas comes in. So let's look maybe a little bit at gas. Gas.go. We have gas costs, which have things like a quick step, a fast step, a mid step, an ext step. I don't know what ext is, maybe external. You can call gas. Call gas returns the actual gas cost of the call, which is maybe different from the estimator. The cost of gas was changed during the Homestead price change, HF. So there's some computation here, and it's actually pretty short, but we're not going to look at it. Here's the interpreter. Oh, there's a gas estimator, but maybe that doesn't matter. So memory is maybe memory in the virtual machine, I guess. So we've got a store. Memory implements a simple memory model for the Ethereum virtual machine. So yes, that's exactly what this is. And we've got last gas cost, maybe the gas cost of the previous operation. And we're just we're going to see like a little bit about where this stuff is. I didn't realize that operations had ACLs, but let's see what kind of ACLs we have. ACLs should be access control lists, I think. So make gas storage func. You pass in a clearing refund uint64. And it's going to, I guess, return a gas func. Maybe gas func is a function that consumes gas, or maybe just knows how much gas it would consume. And we're going to return a function, essentially we're going to return a function. And it's going to take in an EVM object, essentially, presumably kind of like a context, the contract that you're executing, the stack, and the memory to execute on. These are, I guess, kind of like probably essentially the state of the virtual machine, the memory size of what, I don't know if it's total memory or something else. And the function that we're returning is going to return a uint64 of what I don't know, and possibly an error. If we fail, the minimum gas availability invariant, fail 0. So if the contract gas, maybe that's the amount of gas required by the contract, is less than or equal to the S store Sentry gas EIP 2200, we'll return 0 and say not enough gas for reentrancy Sentry. Maybe the thing we're returning is gas left or something along those lines. For example, down here, we're returning cost plus warm storage read cost nil. So this is, I guess, whatever maybe cost was this passed in or figured out somehow? So gas Sentry, I'm guessing Sentry means that this is some like minimum sanity check, and if we don't pass it, we don't do anything. So somewhere we get cost, and we just are, with every operation, we're adding some cost that's like a known cost. So for example, cold sload cost EIP 2929 is being added here, presumably because we have to access something. Add slot to access list. And so is this anything actually related to ACLs? There are access lists, so I'm guessing that it's doing something. I don't know if this is related to authorization or if it's just tracking things that have access so that we can compute the gas. And we're out of time, so we won't find that out. So that's Go Ethereum. The code's super easy to read and to understand. It's organized very clearly. I don't know much about Ethereum. I don't think I've ever read the white paper, but it's actually pretty straightforward. It looks like to understand what the model is just from looking at the code, and the documentation is also good. So those are 2 points, or was it 2 or 3? Some number of points strongly, I think, in favor of this being like a well done software project. Whether Ethereum as a social project is the way that the future will be, I don't know. But as a software project, it looks pretty good.